Welcome to the deep dive. Imagine, just for a second, a really critical piece of machinery, right? Maybe it's on a factory floor, maybe powering a remote wind turbine, and it suddenly just stops. Production halts, costs go through the roof, everyone's scrambling. Now, what if you could, see that failure coming, not just days ahead, but maybe minutes, even seconds before it happens, enough time to actually do something about it? Well, today, we're taking a deep dive into exactly that. We're looking at how to build a real-time predictive maintenance model using machine learning. Our mission, really, is for you, our listener, to get a solid grasp of the whole journey. How does an ML system like this predict equipment failures using all that sensor data, from the raw bits and bytes all the way to, well, preventing problems? It's about making these complex, super important systems truly reliable.
That's right. That's the core challenge we're digging into today. We're essentially going to walk through the whole life cycle, developing the model, registering it, deploying it so it makes predictions, and then, crucially, keeping an eye on it, continuously monitoring it to make sure it works. The goal is predicting those equipment failures before they cause big, costly headaches. And yeah, it involves a lot carefully prepping the data, using things like feature stores to keep everything consistent, managing different versions of the model, serving predictions super fast, and, like I said, making sure it stays accurate over time.
Okay, let's unpack this then. Every journey, well, it starts somewhere, right, with the raw material. So for a predictive model like this, where does all the initial information, the raw data about the equipment even come from?
It's usually a mix, a blend of different streams. You've got real-time sensor data flowing in, maybe from something like a Kafka topic. Think of it like IL telemetry, a constant pulse of vital signs from the machines. But alongside that live feed, we also tap into historical records. Huge amounts stored in cloud data lakes, perhaps Azure Data Lake Storage or AWS S3. This gives us the deep memory, the context of how things performed in the past.
Right, so you've got this torrent of live data coming in, plus potentially years of historical data. That sounds potentially messy. How do you actually turn all that raw stuff into something clean and useful for a machine learning model?
Yeah, it can be messy. That's where the data engineering really comes into play. It's some heavy lifting up front. We take that stream of raw JSON data, for instance, and push it through a processing engine, something powerful like Spark structured streaming. Then comes the refinement. A lot of meticulous cleaning, getting rid of anomalies like, null values or readings that are way off, using tools like PySpark data frames. We also need to create meaningful features. So we aggregate things, maybe calculate rolling averages of temperature over the last hour, or count specific error events within certain time windows. These sliding windows really help capture the dynamics. And finally, we often enrich the data by joining it with reference tables, maybe information about the specific device model, its installation date, stuff like that. All this cleaned, processed, enriched data then lands in a curated Delta Lake table ready for use. And, what's really key here isn't just the basic cleaning, it's the rigor. The real challenge in these real-time systems is catching those subtle issues, the inconsistencies that might slowly creep in and mess up your model without you even noticing. So we enforce a strict data schema, like a blueprint, making sure everything fits. We run automated tests, maybe using PyTest on our transformations. And we do daily quality checks, looking at record counts, null percentages, things like that. It's about building trust in that data foundation.
Okay, so that's the blueprint. If you're dealing with potentially chaotic raw data, that's how you transform it into a high-quality, reliable base. But once you have that solid foundation, what's next? How do you make sure everyone involved, the people building models, the systems using them, are all looking at the same consistent picture?
That's exactly where a feature store comes in. It's absolutely crucial. Think of it less like just a database and more like a consistency engine, maybe.
Yeah.
Its whole point, especially using something like the Databricks feature store, is to guarantee that the features your model trains on are exactly the same as the features it sees when making predictions in the real world in real time. This directly tackles a really nasty problem called training serving skew. It's one of those things that can drive you crazy trying to debug if you don't plan for it.
Training serving skew. Yeah, that
Yeah.
sounds like something you definitely want to avoid. So the feature store basically stops the model from learning on one version of reality and then getting tested on a slightly different one in production. How's that work practically?
Precisely. So we define the structure, the schema, the metadata for our features in the store. Let's say we have a central table for our IoT device features, identified by maybe device ID and the event timestamp. Then we compute those clean features we talked about, using PySpark perhaps, and write them into the feature store. And here's a critical part. We version these features. This means every model version knows exactly which feature version it was trained on. It's vital for reproducibility. And we validate this, of course. We check that features are available for both the offline training jobs and the online real-time lookups. We even run tests comparing the live feature values against the batch computed ones, just to be sure there are no surprises creeping in.
Wow, okay. You can really see how that avoids major headaches down the line.
Yeah.
Having that one reliable version source for features, that's huge. All right, so now we've got these perfectly curated, consistent features. It's finally time to actually teach a model, right? To find those subtle patterns that predict failure. What's that training part look like?
Right, this is where the core machine learning happens. We'll typically use well-established algorithms, often from libraries like scikit-learn. Maybe something like a random forest classifier is a good fit here. They tend to work well on this kind of tabular data. The workflow usually happens in, say, a notebook. We load the training data directly from the feature source C, consistency again. Then we split it into training and testing sets. We train the model on the training set, obviously, and then we evaluate it on the test set, looking at metrics like F1 score, ROC, AUC. These tell us how good the model is at actually predicting the failures without too many false alarms. Now, to keep track of all this experimentation, we lean heavily on tools like MLflow. Think of it as a sophisticated lab notebook for ML. It logs everything automatically, the parameters we use for training, the performance metrics we got, even the model file itself, the artifact. It might store these artifacts in a location like dbfs.mlflow artifacts predictive maintenance. If you zoom out, MLflow is what brings the necessary transparency and reproducibility to the whole process. It's not just about knowing if the model works, but how it works and being able to recreate it. We also do things like cross-validation, maybe fivefold, to make sure the performance is stable. And crucially, we often log model explainability results, maybe using SHAP values.
SHAP values. What do those tell you?
Good question. SHAP helps us understand why the model made a specific prediction, like which sensor reading or historical pattern pushed it towards predicting a failure for this specific event. That kind of insight is incredibly valuable for building trust and for debugging when things go wrong. And of course, we set clear performance targets. We might say, okay, this model must achieve an F1 score of at least 0.8 before we even consider moving it forward.
Okay, so for you, the listener, this means you get a model that's not a black box. You know it performs well, you know why it makes predictions, and it's hit a high bar before it goes anywhere near production. So once we've got this high-performing, well-understood model, how do we manage its life cycle? How do we make sure it's properly governed and ready for deployment?
That's precisely the job of the model registry. It's another key piece of the MLOps puzzle. We'd give our model a name in the registry, maybe predictive maintenance model. This registry acts like a formal library for our models. It manages different versions and, importantly, different stages. Typically, you'll see stages like staging and production. It brings order and control.
Like a promotion pathway for models.
Exactly. So the process involves registering the newly trained model that passed all our checks. We add descriptions, tags like the model version, maybe the date range of the data it was trained on. Then there's usually an approval workflow. Maybe models get automatically promoted to a staging environment for further testing, but moving to production. That almost always requires a manual review and sign-off. Human oversight. This formal process, this registry, is how teams ensure that only the thoroughly validated, approved models actually make it into the critical systems that rely on them. And we validate this step too, confirming all the metadata is right, the right artifacts are linked, and the version history makes sense.
It's like having a quality control gate, or, yeah, like you said, a professional library for your AI. Organized, version controlled. Okay, so the model's approved, it's in the registry. But these models and the data they use are valuable assets. How do we control who gets to access what? Security must be a big concern.
Oh, absolutely. Security isn't an afterthought. It has to be baked in from the start. We need granular access permissions for everything. Take the feature store table we talked about. Data engineers might need read-write access to update features, but data scientists might only need read access for training. Similarly, in the model registry, maybe ML engineers have manage permissions to handle promotions, while data scientists have read permissions to see available models. And then for the actual endpoint that serves predictions, access is typically controlled via secured REST API tokens. Only authorized applications or services should be able to call it. Implementing this usually involves setting up access control lists, or ACLs, within the platform like Databricks Workspace permissions. And for things like API tokens, good practice is regular rotation, maybe quarterly, to minimize risk. It's all about protecting that valuable data and the models built from it.
That really highlights something crucial, but maybe sometimes overlooked, managing exactly who can do what with sensitive data and powerful models. Okay, now for the exciting part. This is where the rubber meets the road, right? Getting those predictions out into the real world fast.
Yes. This is where we see the real-time aspect come alive. The goal is low-latency predictions. We'd use a dedicated model serving tool, for example, Databricks Model Serving, which often leverages serverless compute for real-time inference.
Serverless meaning it scales automatically.
Exactly. It handles the scaling up and down based on load, without us managing the underlying servers directly. We'd set up an endpoint, give it a name like Predictive Maintenance Endpoint. We then deploy the specific model version marked as production in our registry to this endpoint. We configure it carefully, including input schema validation, making sure the data coming in for prediction matches exactly what the model expects. And we enable logging, of course. Logging incoming requests, the predictions made, any errors. This is vital for monitoring later. Validation here involves things like a smoke test, sending a few known examples to the endpoint to make sure it responds correctly. And crucially, we set a performance target for speed. A common target for real-time systems like this is a response latency of less than 100 milliseconds.
Wow, less than 100 milliseconds. Less than a blink of an eye. What actually makes that speed possible? Is it just powerful hardware? Or...
It's a combination, really. Optimized infrastructure, yes, but also very efficient model serving frameworks designed to minimize overhead. The serverless aspect helps too, by ensuring resources are ready instantly.
And what happens if it, slips? Goes over 100 meters occasionally.
Well, an occasional blip might not be catastrophic, but consistently missing that target reduces the window you have to react. The whole point is proactive intervention. That speed allows someone or some automated system to take action before the failure happens. Imagine getting that warning just in time to prevent a costly shutdown. That's the power that speed unlocks.
Incredible. So the model's deployed, it's spinning out predictions at lightning speed. But the job's not done, is it? The real world changes. Machinery wears differently, operating conditions shift. How do you make sure the model stays accurate and useful over time?
You've hit on maybe the most critical part of keeping an ML system alive and valuable long-term, continuous monitoring. It's kind of the unsung hero, because the biggest danger often isn't a sudden total model collapse. It's that slow, silent degradation. The model's predictions just gradually get less accurate, maybe because the input data patterns are slowly changing, drifting from what it was trained on.
Elder drift, right.
Exactly, data drift or concept drift, where the relationship between inputs and outputs changes. So continuous monitoring isn't just about catching outright errors, it's about detecting those subtle shifts. We monitor things in real time. The number of predictions being made, the response latency we just talked about, error rates from the serving endpoint. But crucially, we implement performance drift detection. This involves comparing the model's predicted probabilities against the actual outcomes as they eventually become known. We track key metrics, like that F1 score again. If we see it consistently dropping below our threshold, say 0.75, we trigger alerts.
Do you get a warning before it becomes a real problem?
Precisely. We use tools for this. ML Flow has model monitoring capabilities. We build dashboards in tools like Databricks to visualize trends, and we integrate with alerting systems, maybe Datadog, to notify the right people when performance dips. I actually remember a project before robust monitoring was standard, where a subtle change in raw material quality slowly degraded a prediction model's accuracy by like 10% over 2 months. Nobody noticed until a major issue downstream happened. That's the kind of slow burn disaster this constant vigilance helps prevent.
That's a great example. It really is the ultimate check, making sure your model delivers value, not just on day one, but day after day, month after month. Now, pulling all these steps, data prep, training, registry, deployment, monitoring together, requires some serious orchestration, doesn't it? You mentioned CI/CD earlier.
Absolutely. This whole end-to-end process needs to be automated and reliable. That's where CI/CD, continuous integration and continuous delivery, comes in, integrated tightly with MLO's principles. We use orchestration tools like Databricks jobs to automate the pipelines. Think nightly retraining jobs, jobs that run model validation checks, deployment pipelines that get triggered automatically when code changes are merged in Git. We manage the code and notebooks using tools like GitHub integrated with Databricks repos. This automation isn't just for efficiency, it's for reliability. It ensures every change, every new model version goes through the same rigorous testing and deployment process, minimizing human error. And, in a well-run project like this, every piece has clear ownership. The data engineers own the QA to data pipeline, data scientists own the model development and experimentation, ML engineers handle the deployment and monitoring infrastructure, maybe platform admins manage permissions, and there are timelines, due dates. It's a structured, engineered system.
It really sounds like a complete operational blueprint. Not just building a model, but creating a living, breathing system that's maintained and improved constantly.
Okay, so we've taken quite a journey here. For you listening, hopefully, you now have a much clearer picture of this whole process, starting from that raw, messy sensor data, going through all the meticulous steps of preparation, training, validation, securing it, deploying it for real-time use, and then watching it constantly to make sure it stays effective.
Yeah, and if you connect this back to the bigger picture, this kind of predictive maintenance model is a fantastic example of how modern machine learning isn't just about fancy algorithms. It's about the entire holistic engineering process needed to deliver real, tangible, proactive value in the real world.
Absolutely. So let's leave you with a thought. We've talked about preventing critical equipment failures, which has huge implications for cost savings, efficiency, even safety. But think beyond factories and turbines. What other areas, maybe in different industries, maybe even closer to our everyday lives, could benefit dramatically from this kind of precise, proactive intelligence? Where else could we predict and prevent problems before they happen? Something to mull over. Thank you for joining us on this deep dive today. We hope exploring this structured approach gives you a useful lens for understanding other complex systems, maybe even ones you encounter in your own work or life.